Okay, Illustrative Math, Unit 2, Lesson 23 is called Polynomial Identities, Part 1. So our goal today is I understand what an identity is in mathematics. All right, so our warm-up, calculate the following differences, okay? Should be pretty simple. And then number 2, what do you notice? So go ahead and plug them into your calculator, and let's see what we get. So for the first one, I get 59. Second one, I get 81. And then the last one, I get 35, I think. Hold on one second. My calculator just ran out of batteries. All right, we get 35. All right, what do you notice? Well, if you look at both of these, it seems like, I would say, the difference of the squares of two consecutive, what did I use it? Consecutive integers always equal to the sum of the integers. What it looks like, okay, so the difference of the squares of two consecutive means in a row, is always equal to the sum of the integers. So, 18 and 17, those are consecutive. So the difference of the squares is always equal to the sum. If I took 18 plus 17, so I'll start with, well, let's start with A. A would be 30 squared minus 29 squared. Should be the same as 30 plus 29. Both of those will give you 59. I go down to B, 41 squared minus 40 squared. Should be the same as 41 plus 40, and they're both 81. And then the last one, 18 squared minus 17 squared, should be the same as 18 plus 17. So hopefully you can see the pattern, okay? Now I wonder if that works for any consecutive integers, okay? So let's check this out. Claire thinks the difference between the squares of two consecutive integers will always be the sum of two integers. Is she right? Explain or show your reasoning. So we did it with three numbers there at the beginning, but we didn't really do it like as a proof. So what I'm going to do now is I'm going to maybe do it as a proof. So if I have two consecutive integers, the first one's x, the next one's always going to be one more. And if you look back at these numbers, 30 and 29, 41 and 40, 18 and 17. So Claire thinks the difference between the squares of the two integers. So I'm going to take the bigger one, which would be x plus 1, square it, and then minus x squared, the smaller one. I want to see if that's equal to the sum of the two integers. So x plus 1 plus x. So I need to do a little algebra here and see if it works. So x plus 1 squared is really, remember, it's x plus 1 times x plus 1. So if I wanted to make a box here to multiply that, you got x1, x1, x squared, 1x, 1x, and 1. This will be, I'll come over here, it's going to be x squared plus 2x plus 1 minus x squared equals 2x plus 1 on the right, because these are like terms, I can combine those. And then these cancel, so now we get 2x plus 1 equals 2x plus 1. Since these are equal, your answer is yes, we did a proof. We proved it. okay? And there's my algebra. So it says pause here for a discussion. So if you go back here and you just do it with numbers, we're not necessarily proving it for all numbers. We're proving it for 30 and 29, 41 and 40, 18 and 17. If you use letters and do the algebra and you get them to be equal, now we're proving it for everything. Remember, consecutive integers are always going to be x and then x plus 1, okay? And then if I had 3 consecutive integers, the third one would be x plus 2, and then the fourth one would be x plus 3, and so forth, okay? All right, if I go down here to number 3, let's see if this one would work. Andre thinks the difference between the squares of 2 consecutive even integers will always be 4 times the sum of the 2 integers. Is he right? Explain or show your reasoning. So even integers or odd, your first one's going to be x, your next one's going to be x plus 2. Okay? Erase that. All right, why? Because think about consecutive even or odd integers. The next odd number after 3 would be 5, so it's 2 more. If I had even numbers, the next even number after 4 would be 6. Pick another pair of even consecutives. 12. The next even consecutive would be 14. It's always 2 more. Okay? All right, so let's see if we can write the algebra. The difference between the squares of the 2 consecutive integers. So it's going to be x plus 2 squared minus x squared. And I'm going to put this one first because that number is greater than x because it's 2 more. Will always be 4 times the sum of the 2 integers. So it's x plus 2. I want to see if these are equal. So if I multiply x plus 2 and x plus 2 in a box here, what do I get? I get x squared, 2x, 2x, 4. So that's going to be x squared plus 4x plus 4 minus x squared. 4 times 2x plus 2. And then distribute here, I get 8x plus 8. These cancel. So I could go ahead and finish the algebra. It's not going to always work because this side is not equal to this side. If I multiplied this side by 2, I'd get them to equal, but I can't just multiply half of an equation. I have to multiply this by 2 as well. I have to multiply both sides by 2, and I would see that they're not going to be equal because this would be 16x plus 16, and it's still not going to be equal to that. So that's not going to work. You could also just keep going and solving here if I wanted to. Minus 4 minus 4 minus 8x minus 8x. So what happens here is when you divide by negative 4, the only time that that statement works is when x equals negative 1. That's the only number that it works. And that's not even an even number. So that's not going to make sense. Okay. So this was clearly a no. All right. Back to this one too. If I go to solve it, kind of like I did here, what happens is your x's cancel out and we get 1 equals 1, which this is always true. This is an identity. This is 1 is equal to 1. No matter what I plug in, the left side will equal the right side. So that's called an identity versus a contradiction or just a single solution. All right. So apply the distributive property to rewrite the following expressions without parentheses, combining like terms where possible. What do you notice? Okay. So I do my box, or some of you might know the FOIL method. These end up canceling out, so I end up with x squared minus 1. So these are equal. So this would be called an identity. This is called an identity. So no matter what I plug in for x here and what I plug in for x here, as long as I plug in the same number for x, I will get the left side equal to the right. Okay? Let's go down to the next one. Let's multiply this out. Combine your like terms, and we get, put it up here, equals x cubed. These cancel, minus 1. Okay, so again, this is an identity. All right, so you can kind of see the pattern here. It's always x minus 1 on the outside here with what we're doing here. Then on the inside, it's x cubed plus x squared plus x plus 1, x squared. You see how the pattern, so the next one's going to be to the fourth. So you might be able to kind of follow this pattern here after we do a couple of them. We'll do one more, see what happens. X minus 1, x cubed, x squared, x and 1. So you start to see the pattern here that these end up canceling out. So the only ones that you end up needing are this and that, because everything else pretty much just cancels out. You look here, these cancel out, these cancel out, these cancel out. Kind of like we had up here, these canceled, and so did those, okay? And here we had those. So this is going to equal x to the fourth minus 1. So you might be able to follow this pattern here as long as I'm following that x to the fourth, x cubed, x squared. I'm going down in order and I don't skip anything. I think that this is going to equal x to the fourth minus 1. And then same thing over here. This is going to be x to the 21st minus 1. Okay? Because you're starting at 20 and you're going down. And this is always going to be, oh, wait, hold on. It's going to be one higher. Whoops, hold on. I did it right on the bottom one, but it should be x to the fifth. Okay, so you see how this is always one higher than those two. So you kind of follow the pattern. So these are actually all identities. No matter what I plug in for x on this side, should equal that. Okay? All right, so what is another equation in the form y equals that has the same graph as that? So all I'm going to do is change the form. I'm going to go from factored form to standard form. So if I multiply, I'll do the FOIL method this time. X times x, x times 2, negative 2 times x, negative 2 times 2. These cancel out. So this equation would be y equals x squared minus 4. So this is the same equation. Okay, so if you graph them, they should be equal. All right. I was doing a problem the other night, and I wasn't sure if my answer was right, and it was kind of similar to this. It was actually for a pre-calc class, and what I did was I graphed both equations, and I checked to see if the graphs matched up, and they were the exact same graph, so I knew I was right. So kind of the same idea right here. All right, so how would you explain why x minus 1 times x to the fifth plus x to the fourth plus x cubed plus x squared plus 1 and y equals x to the 6 minus 1 have the same graph? I would say they are the same equation, and I would show it by multiplying. So what I would do is I would take a box and I would multiply x minus 1. I'd put my x to the fifth, x to the fourth, x cubed, x squared, x, and 1 right here. And then I'd get all the negatives here, and I would just kind of say that they end up always canceling out. And I'd say, oh, okay, so these cancel, everything cancels out except for the first term and the last term, and I end up getting these two multiplied together, ends up equaling y equals x to the 6 minus 1. So they're the same equation, just different forms. So they will have the same graph. Now, back to what our goal was I know what an identity is. Well, if I take the first equation, x minus 1 times x to the 5th plus x to the 4th, x cubed, x squared. Oh, you know what? This should have had an x in here. Sorry, I think it has an x in your book. Whoa, I missed that. So, wow, I missed that. Should have had an x. I think it does in your book. Let me double check that, actually. Let me double check your book. Oh, wait, you don't have this one in your book. Okay, so this should have an x. I'm looking at it in my book, and it does. So if you were confused about that, I apologize. All right, there we go. This is equal to x to the 6th minus 1. Okay, so this is called an identity because they're equal. All right, so our goal, I understand what an identity is in mathematics. It's two expressions that are always equal. So here you can write this down if you need it. Identity is an equation which is true for all values of the variables in it. Okay. All right, last thing. For the value, x values of -1, 0, and 1, they tell us that this on the left is equal to x to the 4th minus 1. Does this mean the equation is identity? Explain your reasoning. Does that alone mean it's an identity? No, it means it only works for those values. Now, we can't plug in every number in the world, but we could make a box and multiply this out and see if I get that. So I'm going to just multiply and see if it works out. So I get x to the 4th, negative x cubed, negative x squared, and 1x. Oh wait, this will be a positive x squared. This will be a positive 1x. This will be a negative 1. So when I multiply this out, I get x to the 4th minus 2x cubed these cancel out, plus 2x minus 1. So it's not going to work because it's not equal to x to the 4th minus 1. I have these extra terms in here. So that's not going to work. And you can see how the signs differ there. All the ones we did before, we had all plus. If you go here, they were all plus. So when you start changing the signs, it might mess things up a little bit. So hope you enjoyed this video. Sorry I made that one mistake on the last slide, but at least I caught it. So thanks a lot. Have a good day, and thank you for watching.